talk about the DeepVBA approach, a little bit about its features. Not all can fit in half an hour, but I'll try to make do. So first off, from VBA at the beginning, from Office 95-97, there was like a simple yes or no prompt to enable the macros. First off, what is VBA macro? Like Erez explained before, it's basically an event-based code that runs at the background of Office documents. Okay, we will see an example for that later on. So at the beginning, it was a simple yes or no prompt to enable macros. You can imagine how simple it was to social engineer the victim to just click on that yes or no prompt to enable the macros. That, of course, caused a macro virus era from 95 to 2003, where VBA macro-based attack were pretty popular. Then in 2004, that all ended due to Microsoft policy change. They basically disabled macros by default, making it pretty hard to social engineer the victim to basically cause the cause the victim to launch the code. So that caused the VBA winter when from 2004 to 2013, attackers preferred other ways to attack the victims. Then in 2014, everything changed again. Microsoft basically decided to change their policy and to add this enable content that you probably have seen, all of you have seen, and all of you are familiar. Basically a single enable content after seeing the document. The document is running in protected view and run in a sandbox and probed in a sandbox, but the criminals have found a way to bypass this protected view. So from 2014 to basically present day, VBA macros came back again. They're usually used as a first stage to deliver malware. What I mean by first stage, that means that the VBA macro basically just downloads the second stage of the attack, downloads an executable from online, for instance. Okay, so, and once you download that second stage attack from the web, you can basically do whatever you want. That ranges from banking trojans, ransomwares, APTs, you name it. And recently, Microsoft changed its policy again, right, last month. Basically, what you can see here is the new prompt to enable macros. Basically, end users can still run macros. It just adds extra step. So it remains to be seen what will happen next year regarding the VBA macro vector. So as I said, VBA macros are used as a first stage attack to deliver malwares. There are around 100,000 phishing emails per day that has some sort of an attached Microsoft document. Most VBA macros, as Erez said, use social engineering to just make you click on that content button. Once you click on that content button, it's too late. The code launches and you're going to have a bad time. Current antivirus engines are just not enough. There are too many macros every day. It's impossible to catch up with signatures. And probably most malicious macros are not detected even if they are several months old. That means that a signature-free model is needed to basically solve this issue. And that's exactly where DeepVBA comes in. So before I dive into the architecture and talk to you about deep learning, let's try to understand the problem. So if you manually analyze a VBA macro attack, there are 4 indicators that you want to look for in the code. Okay? So one of them is the code has to be auto-executable. That means that once you social engineer the victim to enable the content, there's no need to social engineer the victim any further. Okay? So the code just launches, and we will see an example for that in Emotet's example, which is an infamous VBA macro attack, which I will present in this presentation. Secondly, the second trigger that you gotta look out for is that the code tries to download an executable or maybe inject a code into a process. That this stage basically symbolizes the attempt of the attacker to download the second stage attack. It tries to download an executable from the web, for example. The third trigger, they also need to execute that payload, of course. They don't necessarily do it immediately. Sometimes they schedule it in like an office update or something like that. And they schedule it for a later time because they want to evade the probing mechanism of the protected view of the sandbox, which tries to probe the document and runs the code and tries to see if something fishy happens. And the fourth trigger, which is really, really common, is that they usually obfuscate their code. So for those who do not know, obfuscation means that they just scramble the code, just shift it around, make it look really, really weird. and we will see an example for that later. They usually do that to hide their intent and make it hard for analysts to understand what the code is actually doing. So all these 4 triggers, and you can say that a suspicious sample is one that it's auto-executable. It has to run. It probably runs automatically, and it triggers one of the other triggers. Okay, so let's get a little bit more intimate with the issue. So I'm gonna present an infamous example, an infamous VBA-based macro attack called Emotet. It was first identified in 2014 as a backing malware stealing private information. And also note that it was in 2014, right after Microsoft changed its policy. So which is interesting to see how Microsoft policy changes affect the whole world. So it's still active till this day. It was recently used as a service, as an infrastructure as a service for delivering malware. That means that criminals buy that infrastructure to basically initiate their own second stage attack, their own payload, their own criminal activity. So the most common entry vector of Emotet is, as I said, an attached file that is usually arrives at the victim through some spear phishing email. Now you can see here that it was arguably considered the world's most dangerous malware. In January 2021, that means from 2014 to January 21, it was still an issue for the whole world. And it took all these states to collaborate in order to bring it down. And it's still active today as an infrastructure as a service. It has a 3-stage workflow. First, it is delivered to the victim's computer via spear phishing email. The victim is then prompted to download that file and basically just click on enable content. Once that happens, the computer becomes vulnerable and it can be offered for hire for other criminals. And that fact makes it really, really hard to keep track of Emotet once you pass that initial vector of attack. Once you click on enable content, it's really hard to stop that attack because it can be anything. Okay, it can open doors for all kinds of attack, from information stealers, Trojans, ransomware, and many, many more. So just a general note, not regarding this presentation, just how to protect yourself from these kind of things. So if you receive an email from an unknown sender with some sort of attachment, be wary of it, especially if it has a sense of an urgency or maybe it offers you $1 million. That doesn't make any sense. So please don't download attached file from strangers. So here's a real life example of how an Emotet attack looks like. So this is the spear phishing email. The very first time you encounter the Emotet in the wild, you receive an attachment, you receive an email in your Outlook account of your organization. It tells you, oh, you have to pay something. Never mind what it is. You just have to pay it. You just have to pay it right now. A sense of urgency indeed. Once the victim downloads the attached file and he has to see what he has to pay. He has this sense of urgency. He just clicks enable content right away. And once he enables that the content, the code launches. Now that's where we dive in. That's what we're interested about. We're interested about analyzing the source code and not analyzing the document and the email. DeepVBA just looks at the code itself. And on first view, it looks kind of hard. What is happening here? Okay, this is really Emotet's code. A small part of it talked about obfuscation. For those who do not know, that's how obfuscation looks like. You just look at the code and you don't know what's happening. That's when you know you have obfuscation. So the code is highly obfuscated, and we're manually analyzing this code. So we have to search for those 4 triggers. So I made it easy for you. I already searched for them. So you can see that the document open, which is an event-based, as I said, VBA is an event-based code language, and document open, these API calls, which are event-based, cannot be obfuscated. Okay, so here you go. You can see here that the code is auto-executable and the obfuscation signal is plain to see. So after a cumbersome manual analysis, I won't do it right here. I've done it before. The code, basically what it does, you can see here, it launches a PowerShell process that later on downloads an executable and launches it. Okay, so that's all the 4 triggers right there. But you can see that we had to manually de-obfuscate this code in order to get these triggers, right? So how do we catch that signal without de-obfuscating the code? We will get to that later, how DeepVBA does that. So just to get the idea of the obfuscation level here, you can see here the line of code which was initially the obfuscated code, and after a lot of deobfuscation effort, it was transformed into this, which basically just zooms in. If you want, I zoomed in into what really happens here. You can see that it's running a PowerShell and then just runs a code that downloads something from online and actually then executes it. But when this code launches, it's already too late. Okay, I want you to remember this get object. Okay, these get object API calls cannot be obfuscated, and I just want you to remember that. I will get into that. I will get back to it in the following slides. Okay, I already talked about this. Okay, just to summarize Emotet before we continue to the DeepVBA approach. The initial vector of the attack is a VBA macro, which is attached to malicious documents. In this instance, the VBA macro runs a PowerShell process that downloads and executes an executable code, whatever. It could be anything. The second stage attack can be pretty much anything. Think about it as an open source library for criminals, okay? Eventually, what this in this particular case, the executable opens a backdoor, and then criminals can install whatever they want. They basically own your computer. So how does current approaches try to detect the VBA macro? Based on the code itself, okay? We're just trying to look at the code and understand what's happening. So most attempts try to use some handcrafted features or maybe handpicked words combined with some sort of basic classifiers. But other than those features are handcrafted and cause a bias into your model and into your solution, they also have a big disadvantage, which is that the features are computed on the code as one single chunk. And I remind you, when I showed you the Emotet's example, all that code is one single chunk. It's really hard to understand what's happening. It's really hard to understand what is the initial entry point. And moreover, a lot of attacks use evasive maneuvers, where they just add meaningless functions to evade detection. So you can think about it, if you look at the code as one single chunk, you're gonna have a bad time. It's really hard to understand what's happening. It adds a significant amount of noise. And that's exactly what DeepVBA tries to solve. Basically aims to identify these 4 suspicious triggers, while overcoming non-evasive maneuvers, minimizing the noise in the input, being a signature-free model, and also a lightweight model. Okay, so that means you can't just throw GPT-3 on it. It won't work, because eventually this project needs to basically work on every document that you receive through email. Okay. So what DeepVBA does is basically it utilizes the code graph structure and the VBA macro code itself of each function separately and then jointly, and tries to identify the VBA macro as malicious or benign. Now, let's see what I mean. So DeepVBA uses an open source library called VBA2Graph, which was developed here at Checkpoint by our very own security expert, Michael Abramson. VBA2Graph creates a call graph from the VBA macro, and you can see it here. This is Emotet's example. After I ran a VBA2Graph on it, and you can see it's a lot easier to see it like this. You can see the document open, the initial entry point, all these red frames. It's kind of hard to see from the presentation, but that means that this graph, this connected graph, there could be other disconnected graphs, but in this case, there is only 3 functions, and you can see that all of this graph is auto-executable. Also, what VBA does is also marks some suspicious keywords and API calls. And remember when I told you to remember that get object? So here it is, that get object. It wasn't in the obfuscated line of code, but it was somewhere else. Okay. So, and all these other C bytes and all these char Ws are usually used as attempts to obfuscate your code. Okay. So what you can see here is basically that the attacker, just from the get-go, just from this feature, just from the keyword sequence right here, you can already understand that I have an obfuscated signal. I have an auto-executable signal. And I also have something, it tries to initialize some sort of object and do something that it tries to hide its intent. So that's already a good feature that helps us extract these signals. So let's talk about the DeepVBA architecture, just the overview. We'll get back into each single model, try to talk about it. We don't have enough time, but I'll try to make do. So at the beginning, we have a call graph, and the number of features for each function is different, okay? And I need to bring it into a fixed size representation in order to aggregate the nodes together, okay? So how do we do that? We basically use a module called node embedding the node embedding is run over all the nodes in parallel and outputs a single fixed vector representation. In the next slide, we'll talk about a really cool feature that we are using other than the keyword sequence in the node embedding. After we have a fixed size representation for each function, we can run it through a graph neural network approach, which is basically like a convolutional layer, only that the spatial filter here is not the neighboring pixels, is the neighboring nodes. Okay? So after the graph neural network, we still have a graph presentation. And remember, this call graph, we eventually want to have a malicious score. Okay, so this is a graph-to-one architecture. So we use an attention layer that has a cool side effect that it emphasizes suspicious functions to basically clamp it down into a single graph embedding. That graph embedding is then fed into a few linear layers to output the malicious score. Okay, so let's talk a little bit about node embedding. Okay, so the node embedding receives all the features of the function. You see in one of them was the keyword sequence. It has also the auto executable, which node is auto executable, and it has two other features that I will discuss in the next two slides, and that is the code token sequence. Basically, what we're doing is we're trying to identify the obfuscation signal, but not only. Okay, so how do we do that? We use a byte pair encoding tokenizer, a BPE tokenizer, and we use it and we train it on our database, of course. And remember that usually the database for the cyber domain is unbalanced. You pretty much have 95%, 99% benign, and 1% malicious. Okay? So when you train it on our data, it kind of acts similar to Huffman compression. We will see what I mean. Okay? So basically, as I said before, most malicious examples are obfuscated. So obfuscated code will be harder to compress, and that's because the tokenizer, the BPE tokenizer, his merge rule is based on frequent words. And you can imagine then that this long-ass word is not frequent in our data. Okay, it's generated. It's randomized. So here you can see like an example. I just fished out a random malicious sample from our database, and then I ran our trained tokenizer on that function. And you can see that it's made up of specific tokens, and those tokens are the base tokens, okay? It's not comprised of the call or the at, which are frequent words. Most of it is the base vocab tokens. And we will see how different the distribution over the tokens in the next two slides. Just to clarify, the X's and the V's are a special token. The X's symbolizes a number sequence. We're not interested to learn which number it is. We're just interested to know that there was a lot of English letters and then some random numbers. That's how we try to extract that obfuscation signal. And the V's just mark a line drop. You can see that a new line has begun. Okay, so here I talked about the compression. I talked about Huffman compression. What does that have to do with the tokenizer itself? So here we can see the distribution between the benign and the malicious compression ratio. That means that I took the number of tokens that symbolizes a function and I divided it by the length of the string. And you can see that, as we assumed, the compression ratio for the benign will be a lot better. That means that we managed to compress benign sample to 25% of the original size, where the mean for the malicious samples was 35% of their initial size. That means that it's harder to compress obfuscated signals, okay? So that's the compression ratio, which is just a scalar, is also one of our most significant features. And you can see this overlap right here. And this overlap is exactly those evasive maneuvers that I talked about. They just add benign functions that look seemingly innocent, but basically some other part of the graph is doing the malicious work. Okay, so here you can see the wide difference between the benign token cloud and the malicious token cloud. And you can see, as I said, malicious tokens mostly made of base vocab characters. But what I mean by base vocab characters is the B as the E as the C as the F, where the benign token cloud is made up of frequent English words that we are familiar with. So I talked about the node embedding model. There's a little bit more features to it. It's a bit more complicated than that, but I won't get into it. So after the node embedding basically ran on our call graph, we have now a fixed size representation for each function. And we want to now we have an embedding for each node separately, but we still want to aggregate the information between the nodes because the document open in Emotet's case called the second function but so far they haven't exchanged information between the nodes. So what we have is a graph neural network that basically acts as a special kind of convolution. As I said, it aggregates information between neighboring nodes. What we use in our current architecture is a layer called a graph convolutional layer, and you can see the message passing here. Message passing, by the way, is a mechanism that graph neural network used to aggregate neighboring nodes. And in this particular case, the equation looks like this. Basically, you have the theta weight matrix, and I is the focal point, is the central pixel. If I use the analogy to convolutional layer, Ni is the neighboring pixels, okay, the neighboring nodes in this instance, and K is just the index of the layer in the whole architecture. And you can see here that we also divide each node embedding. When we aggregate it, we normalize it by the degree of the node, okay? So after the graph neural network, we still have a graph, and we still want to compress it to get a graph embedding. So we use an attention layer. So the attention layer, what it basically does, it outputs a probability distribution over the nodes, and then we use that probability distribution in order to do a weighted average over the nodes to get a single graph embedding. And there's a cool feature to it, is that the probability distribution, as you can see here, I ran our model on the Emotet example. It, of course, detected it as malicious. And also, he decided to give a uniform distribution over the malicious nodes. That's because all of the nodes are malicious. But what will happen if I will add benign functions to it? Let's see. So I added some benign functions that I wrote myself. Okay, it basically just orders around the column in Excel, pretty benign, nothing suspicious about it. And I ran it as one single function, as one single sample. And you can see here that still the model basically learned the attention layer gave more weights to the malicious nodes, which were in this case the Emotet functions, and gave smaller weights to the benign functions. So that's a cool way of us to also augment our data. We can then later on use benign functions to augment our data and then enrich our malicious database. And also it adds to explainability. That's a cool feature. So we reached the summary with even 5 minutes to spare. So more time for questions. So at the beginning, you have a spear phishing email. You download the document and then you're prompted to click on enable content. Once you do that, the code launches. Okay, so before the victim receives the email, in one of Checkpoint's engines, we basically extract the code before it reaches your computer, and we take this code, the string of code, and we use VBA to create this code graph you see here, and then we feed it into the VBA to get a malicious score. Okay, and that's one of the features that we're using at Checkpoint to protect your computers from attached malicious documents. Okay, so that's it. Thank you. And there's also 5 minutes to spare. So if you got any questions, I'll be happy to hear them. Yes?
If you are using the graph, why don't you run the VBA on the weakly connected parts of the graph and not the whole graph as a whole?
You mean, what do you mean by weakly connected? You mean
separate the whole graph into weakly connected components?
Yes, to cluster it to the cluster of the graph.
Yeah, well, it's an interesting thought. We haven't tried it yet. I can tell you that the variance here is pretty large. Okay, each malicious looks different. Each benign sample looks different, and we try to extract the information for the code itself. Okay, so if I understood your question, you basically said you have those weakly components apart in your graph.
Basically, different programs that are unrelated to one another.
Well, I can tell you that you can't really know that, okay? Because you can have we had the document open right here, which was the Emotets, but there also was an auto-executable functions that was the on the workbook open. Okay, so maybe that was the benign and that was the malicious. You can't really know.
Yeah, but what I meant, if you separate into weakly connected components, you can say that this component is malicious and this component is benign. So it will be pursuit, and so a weak and benign component will not masquerade some of the data that.
Yes, that's an interesting thought. We haven't tried it, and we'll look into it in our research. Of course, this is a project that we run like 7 months, 4 months, 5 months. So there was a lot more to research, and I like that idea to look at the weakly component. We haven't yet actually looked at the graph properties of each sample. We just try to extract the best node embedding we can from each node. But the graph structure also has valuable information. We haven't even scratched the surface in that regards. But it's an interesting idea. Yes?
You said lightweight. So how much pre-processing time it takes to actually extract that graph and then run it? Like, how lightweight is it eventually? Is it like eventually?
We're aiming to hundreds of milliseconds. That's our aim. The whole pipeline. Of course, the input is variable length. Okay, because you can have graphs of 2 functions. You can have graphs of 5,000 functions. And it's interesting to ask, how do you truncate your input right now? Because maybe you truncate the malicious part and just remain with the benign part. So it's a pretty interesting question, how to truncate the graph.
Just ballpark, how bad or how good is it now?
So the variance here is if you take all these, if you don't put a limit, then you can reach even 10 seconds.
In practical use?
To hundreds of milliseconds. Yes, that's the mean.
Okay, but there is you're still researching how to prevent something like a DDoS attack by using big data. It's like, because you told me the graph can be big. Yeah, the graph can be pretty large. So we're still researching how to basically truncate it and still maintain the malicious, to not accidentally delete the malicious nodes. Currently, we're still tackling this issue of the really, really large graphs. I would say the silver lining here is that it's the micro percentage of our data, those really, really large graphs. So it's interesting. It's not that interesting as a statistically interesting, because most of the samples, if you get an attached document with thousands of functions, the document will be pretty large. So also, it's statistically, we can ignore it for now. So you're thinking about how to scale it up, basically?
Of course, it's one of our questions to ask: how to truncate how to truncate really large graphs.
Yeah, thank you.
No problem.
Cool.
Yes. It seems that in your node embedding, you made a separation not between malicious and benign, at least at the level that you told, but between obfuscated and non-obfuscated code. So aren't there like benign VBA scripts which are obfuscated, and there will be, it's not a binary classification, but it will get the same embedding as as malicious scripts and get.
That's a very good question. Because we try to identify that obfuscation signal, and we say it's one of our triggers. But indeed, a benign sample can also be obfuscated, but it's not. It's 99.99% of the times it's not the case. And if it is, then it should be detained at the border, so to speak, for further analysis. Okay. So yeah.
Do you have a confusion matrix to classify this to understand who's using?
Yes, we are currently around, I won't tell you all the data, all these metrics, because we just don't have enough time to discuss it. Also, it's not that plain and simple. What the POC objective was, which we passed, was around 95% precision and 40% recall. Now remember that our reference verdict is one that was computed over dynamic analysis. That means that someone actually ran that code, looked at the document, looked at the email, had that all information, and then made a decision. So reaching 40% recall only on the code itself is a pretty good feat, to my opinion, at least. Yes, way back there. Oh, so Yaakov here asked that question, the latency. So I'm sorry. I'll repeat the answer. The mean area for the latency is hundreds of microseconds. Of course, there's a lot of optimizations that can be done. Okay, this is still just past POC, so there's a lot of optimizations that you can do. But the model itself is pretty small. It's around 5 megabytes. Okay, and it can also be smaller.
Does that include preprocessing?
Yes, that also includes preprocessing. Of course, as I said, the input is variable length. So if you get a huge sample, then of course it will take a lot more than 100 milliseconds, than hundreds of milliseconds. But that's not the case 99% of the times. Okay, so back there. Yeah, so the attention mechanism right now is a simple mechanism. It can be better, it can be improved, but the idea is to use, the idea of using the attention layer to aggregate a lot of vectors to create one single embedding is not a new idea. So I just used it. And sometimes it acts as an explainability mechanism, but currently I'm just using an hierarchical attention mechanism. In the future, I would like to maybe try a self-attention, a transformer layer, but it remains to be seen. Thank you for listening. Had a great time.